In lecture 34b, I introduced the very cool idea of a Laplace transform for solving linear differential equations. We continue that here in lecture 35b, Laplace transforms for linear differential equations to help you solve them. We'll look at the example from 34b, but we'll also look at a new example with a discontinuous quote-unquote forcing function. I put quotes around the forcing because it's not forcing in the usual sense that we've talked about. It involves a discontinuous function called a unit step function. That kind of represents switching on a light bulb, so to speak, flicking a switch like an electric circuit. Laplace transforms are a nice way to handle that. We'll also look at a new property called the shifting the origin on the t-axis property, a very strange name for the property, but it is what we will use. So let's start with the example from lecture 34a. We didn't quite finish it. Let's finish it now. Here was our first order non-homogeneous linear IVP. Is it forced? Is e to the negative 2t a forcing function? Well, you could think of it that way. However, it's a first order equation, and usually when we're thinking about physics and Newton's second law, we've got a second order equation for the acceleration is the second derivative of the position. I suppose y could be the velocity instead of the position, and then you could think of it that way. But we usually don't. I'll call it forced anyway. It's certainly non-homogeneous. It's a non-zero quantity on the right-hand side. We talked, big overview of the method for using the Laplace transform to solve this. Let's go into the details now. I've got more steps this time. You start by taking the Laplace transform of both sides. Is that allowed? Well, realize what you're doing when you solve such an equation is you're really assuming y is some function of t where this is true, where the derivative with respect to t plus 5 times the function itself always equals e to the negative 2t. So I'm really kind of assuming I got a function and I'm trying to derive what it would be if I assume there is one. It's not a guarantee that there is one. That comes in the checking. But that is the basic logic. So I'm assuming there's some function that I plugged in there, and now I can take the Laplace transform of both sides because by my assumption these are two equal functions of t. You don't see the explicit dependence of t right there, but you imagine it to be there. I said in lecture 34b that the Laplace transform is linear. It's a linear transformation on function spaces. What function spaces? We're not really saying, okay, because that would be a bit too technical for us. But the Laplace transform of a linear combination is the corresponding linear combination of the Laplace transforms. So the Laplace transform of the derivative plus 5y would be the Laplace transform of the derivative plus 5 times the Laplace transform of y. We also evidently need to figure this out, which I did do in the last lecture. In the last lecture B, I derived that the Laplace transform of e to the at is 1 over s minus a. It's a function of a new variable called s. It equals this, where a is a constant. As long as s is bigger than a, our improper integral that defined the Laplace transform would converge. You don't typically need to worry about the domain so much. Just focus on the formula. In this case right here, a is negative 2. So 1 over s minus a would be 1 over s minus negative 2, which would be 1 over s plus 2. And notice the linearity used on the left. Second important thing you need here is how the Laplace transform affects derivatives. I talked about that in lecture 34b as well. The Laplace transform of the derivative of a function, of a nice function that you can plug into the Laplace transform in its derivative, was s times the Laplace transform of the function minus the initial condition at t equals 0. This thing right here became this thing right here. How did we derive that? We used the definition of the Laplace transform in terms of an improper integral. I'll put it up on the board to remind you. The Laplace transform of a function, little f of, say, t. I'll put the t in here explicitly there, though I don't always do that, including in this lecture. I don't always do that. I'm not doing it here for one thing. Is by definition the improper integral from 0 to infinity of little f of t times e to the negative st dt, where when you use the formula you think of s as fixed. But when this integral converges, The answer's got to depend on s, because there's an s in there that is I'm treating like a constant when I do the integral. But the final answer depends on s, so you can think of it as a function of s. Why s? Well, it's just the letter that people picked. Turns out we saw that if you use integration by parts, the Laplace transform of a derivative can be written as s times the Laplace transform of the function minus the initial condition, if we assumed that the function was nice enough it didn't grow too fast. That was an assumption. So essentially, the Laplace transform is converted differentiation to arithmetic or algebra, involving subtraction, multiplication, and evaluation of a function. Continue. How? Solve this algebra equation for the Laplace transform of y. Add y of 0 to both sides to cancel here, meaning add 3 to both sides. And then these two terms have a common factor of the Laplace transform. It can be factored out, and you're left with s plus 5 times the Laplace transform of y. Divide both sides by s plus 5. So there's your 1 over s plus 2 from there. Plus 3 came from adding y of 0 to both sides, which was 3 to both sides. And then divide the whole thing by s plus 5. Simplify. You can break this fraction into two pieces and combine these denominators into a product in this denominator here. You can check that. Plus 3 over the same s plus 5 that you see there. We now want to take the inverse Laplace transform. That was the third key step, and that's a linear transformation as well. But to help us do that, we need to use partial fractions to help us rewrite this fraction in a way where we split it into two pieces where the denominators are simple, because then we can use this fact again, that the Laplace transform of e to the at is 1 over s minus a. That could be used if we just had these simple denominators, s plus 2 by itself or an s plus 5 by itself like we do here. Quickly go through the partial fractions on the board. It's not on the PowerPoint. We're looking for constants a and b where this is true, for all values of s in this case. Trick, multiply both sides by that common denominator to get complete cancellation on the left, partial cancellation on the right. The technical best way is to solve this is to expand things out and equate coefficients of like powers of t. However, it's quicker, especially in simple cases, to just plug in some particular values of s where these things cancel here and here. Like if s is -5, this term goes away. You're left with 1 is b times -5 plus 2 is -3, so b must be -1/3. When you plug in s equals -2, this term goes away. You're left with 1 equals a times -2 plus 5 is 3. So a is +1/3. Is that really allowed? I mean, these fractions are not defined when s is -2 or -5. Well, it turns out it works, okay? You can double check it by plugging these numbers in up here and then adding the fractions by getting a common denominator. So there I have it right here. There's my a, +1/3. Notice it's over s plus 2 like it is on the board. There's my b, -1/3. It's over s plus 5 like it is on the board. Don't forget about this term. That goes over here. And then these two terms can be added. Add the numerators. -1/3 plus 3 is -1/3 plus 9/3 is 8/3. Now take the inverse Laplace transform of that expression and we'll be done. We did use the initial condition, by the way. We used it by plugging y of 0 equals 3 in to this equation here as we solved for the Laplace transform of y. But now take the inverse Laplace transform. Y is the inverse Laplace transform of a Laplace transform of y. They are inverse functions. But we have just found that the Laplace transform of y is this entire thing here. The inverse Laplace transform, I said, is a linear transformation as well. You can, we've got a linear combination of functions here. I can bring the constants in front, the 1/3 and the 8/3. And then these two things are inverse Laplace transforms that I can compute because of this fact here going in reverse. The inverse Laplace transform of 1 over s minus a is e to the at. Okay, that's what I used here. With this one, a is negative 2, so I get a negative 2t. With this one, a is negative 5, so I get an e to the negative 5t. We should check the answer. Here's the work that checks it. I'll leave it to you to check that work. I did left-hand side ultimately equals right-hand side, and I also checked the initial condition. Also might be a good exercise to check this with either integrating factors, with the original equation, or the method of undetermined coefficients. You should get the same final answer. Math is consistent. How beautiful. All right. Let's go on to the new example involving a discontinuous forcing function. This is the example. What's the discontinuous forcing function? It's this thing here. What is that? U2. Well, it's not the band U2. It's not U2. It's U sub 2. It's called a unit step function that has a value of 0 when t is less than 2 and jumps up to a value of 1 when t is greater than or equal to 2. The 2 tells you where the jump discontinuity occurs. U3 of t would be 0 when t is less than 3 and jump up to 1 when t is greater than or equal to 3. I'm also going to write the equation like this and emphasize that I can think of this expression right here as an f of ty. Why am I doing that? Because I want to also make the slope field ultimately for this solution in this differential equation. We can think about slope fields here. Back to chapter 1 in a sense. Yeah, u2 of t is 1 if t is greater than or equal to 2 and 0 if t is less than 2. Could I make this a greater than and this a less than or equal to? Well, yeah, I guess you could if you wanted to, but this is standard. It's called the unit step function, also called Heaviside Function, in honor of somebody named Oliver Heaviside, with jump discontinuity at t equals 2. If you graph it as a function of t, it's 0 when t is less than 2. Put like an open circle right there to emphasize the point 2, 0 is not on the graph. Then it's 1 with a filled-in circle right there when t is greater than or equal to 2. The filled-in circle just emphasizes that the point 2, 1 is on the graph. This is u2 of t. Yeah, like I mentioned before, this might represent flipping a switch at time t equals 2, like in a little electric circuit. You might have a switch that turns off the on and off the current or something, or the voltage. But wait a minute, is that really a discontinuous operation? Isn't there, I mean, it's got to move, doesn't it? Here's a general principle. It is often easier to model almost discontinuous phenomena in real life with actually discontinuous functions. Instead of trying to create a function, say a nice smooth function that's 0 up until, well, really close to 2, and 1 once you're at 2 and greater, that still passes the vertical line test, even though I'm drawing it almost vertical here. To come up with such an example function, that'd be a big pain. It can be done, but it's much harder than you might imagine. It involves something called bump functions, if you want to look that up. Bump functions. It's a difficult kind of thing. So it's easier to just use a plain discontinuous function, an actually discontinuous function, to model almost discontinuous real-life phenomena. Evidently, though, if we're going to use the Laplace transform, we better know the Laplace transform of such a function. Here's I'm about to show you the calculation. Maybe you want to pause the video, try it yourself. It is important to use the formula for UA of t in general, or U2 of t in particular. Here it is. The Laplace transform of U sub a of t, this is the unit step function with jump discontinuity at t equals a. I'm assuming implicitly here that a is greater than or equal to 0. I write this. There's the definition of the Laplace transform. What do you do with that? How do you integrate that? Use the formula for UA of t. It equals 0 when t is less than a and 1 when t is greater than or equal to a. So the product of these two things is 0 when t is less than a. You can just integrate from a to infinity 1 times e to the negative st, because the function UA of t is 1 when t is greater than or equal to a. So now the integral becomes simpler, and remember, improper integrals are really limits. I'm really thinking about, does this limit converge? Does the improper integral converge? You can check all this. It converges to this, technically speaking, for S positive, for this to work. However, again, the domain we don't typically have to worry about, okay? I personally have never worried about the domain other than just to say, hey, that's the domain on which this improper integral converges. Okay, so remember this. Put it on the board here. The Laplace transform of the unit step function with discontinuity at t equals a, we have just found to be e to the negative as over s, where a is a constant. S is the variable for the Laplace transform itself. Okay, good to have that on the board. Good to have the other one on the board too, the inverse. Therefore, the inverse Laplace transform of e to the negative as over s, they undo each other. This is ua of t. It's easy to derive Laplace transforms of functions. It's only easy to go backwards with the inverse transform if you already know the Laplace transforms to begin with. It's kind of analogous to differentiation and integration. It's sort of easy to straightforwardly differentiate something, but to integrate back, to find an antiderivative, you've got to know some things, memorize some things about differentiation, plus some other techniques. Thus, what? Thus, now let's actually solve the differential equation. Apply the Laplace transform to both sides. That is the same equation. Yeah, okay. I had a 5 there originally, but I wanted to change it to a 1 coefficient of y there because I wanted to be able to see the graph more nicely, which I'm going to show you. Take the Laplace transform of both sides. Use linearity. Use the fact that the Laplace transform of a derivative is this again. Plug in 3 right there again. It equals the Laplace transform of the right-hand side, which is this. A is a 2. A is 2. Solve for the Laplace transform of y. It's an algebra equation to solve. There it is. What did I do? I added 3 to both sides. Then I divided both sides by s plus 1 from these two terms. Get that? Hey, this is looking good again. Well, or is it? Now I've got this e to the negative 2s up there. Can I do partial fractions? Yeah, but the partial fractions will still involve a factor of e to the negative 2s in front of the fraction if you like. Do it anyway. I did. 1 over s times s plus 1 turns out to equal 1 over s minus 1 over s plus 1, but I still have the factor of e to the negative 2s to put in there. So it still seems to be a problem. Or is it? This one's not actually a problem. I can use that. Its inverse Laplace transform would be u2 of t. But this one is a problem because we don't have a plain s down there, we have an s plus 1. I could write this, but how do we, this is the hard one right there. How do we do that one? These two, we know. How do you do that? We need a new property. How to compute these first two terms. Okay, well, I've told you how to compute the first one. When I was making the PowerPoint, I wasn't thinking about putting this on the board necessarily. There's how to do the very first one, but what about the second one? We need a new property. It's called the shifting the origin on the t-axis property, a long-winded name, descriptive name. Suppose the Laplace transform of little f is capital F. I could have put little f of t, decided not to. Kind of a good reason for that in a sense. Suppose we know that. Sometimes in math you just have to play around with things and just see what happens. Evidently Laplace, or somebody after Laplace, was experimenting with functions and unit step functions, maybe Heaviside maybe, and maybe multiplying them and wondering what the Laplace transform would be. Like, what is the Laplace transform of ua of t times, I could put f of t in here, but it's going to be more useful to put f of t minus a horizontally shifted version of f on the t-axis to the right if A is positive and to the left if A is negative. I am allowing A to be negative there, I think. Though, well, I guess for our applications A is positive. And that does make sense in terms of the integral too. It's a rightward shift of the graph of f, multiplied by the unit step function. In other words, if you graphed this product, if the graph of f looks like this, say, that's f of t, the graph of f of t minus a, if this is a right here, is going to be similar, just shifted to the right, something like this. And, okay, I guess there'd be a piece of the graph initially to the left of the vertical axis in the first picture. Let's say it looks like this over here. I'd also have this over here. But then the graph of UA of t times f of t minus a is right here, is going to look like this over here still, but it'll be 0 here, because that'll be 0 when t is less than a. That's the function we're thinking about taking the Laplace transform of. First, the definition, to get that. Second, the fact that UA of t is 0 when t is less than a, so yes, I'm implicitly assuming a is positive here. And 1 when t is greater than or equal to a, so I got a 1 there. But how do you do that integral? Or more importantly, how do you relate it to the Laplace transform of little f? Do a substitution. I don't think I want to call my substitution u because I'm already using the letter u. Let w equal t minus a, so t is w plus a, and dw is dt. And every time I say dw, I think of Arthur. You know what I mean? Okay. Look up Arthur and dw, you'll see what I mean. So there, t minus a gets replaced with w. T right here gets replaced with w plus a. dt gets replaced with dw. Now we have a complication, it seemed, right there. It's a w plus a instead of a w inside the parentheses. Well, then this is the same as e to the negative sw times e to the negative sa. And e to the negative sa doesn't depend on w. It's a constant with respect to the integral. I can put it in front of the integral. That's what we do here. And write it as e to the negative as instead. And then we've got this. Integration variables are sometimes called dummy variables. It doesn't matter what they are. W and w and w instead of t, t, and t. This is still the Laplace transform of little f. Doesn't matter that I'm calling my variable of integration w, which I'm assuming to be capital F. So the Laplace transform of this is that, and therefore the inverse Laplace transform of a function of the form e to the negative as capital F of s is ua of t times little f of t minus a, where you're assuming in this that the Laplace transform of little f is capital F. There it is. And hey, in the previous slide we had something over s plus 1. The something on the top involved e to some power of s. We're going to use that now. Right here. The a is 2. For this here, it's a little confusing. This a is 2, negative 2. The a down here is negative 1 when I want to use this property. So I'm using a in two different ways, and they're different values here. To use this property, think of the a as negative 1. So when I take the inverse Laplace transform, I get this right here. Notice how these match. Or did I make a mistake? Oh, excuse me. Yeah, I made a mistake in how I was describing the a. The a for this property is 2. The a here, negative 1, corresponded to these two properties. Would have been good to use a different letter. So yeah, compared to this, the a here is 2, so we get a sub 2. We also get little f of t minus a, e to the negative 1 times t minus 2. The most common place people make a mistake here is they just put a t, negative t there instead of a negative in parentheses t minus 2. That's the most common mistake. You gotta have this t minus a there. That's the most common mistake people make. You can write this in other ways. I don't know where that green dot came from. Why that's not erasing anymore. I still don't quite understand smartboards. A couple other ways you could write it. Whether they're useful or not is kind of in your own mind. Probably best just to leave it like that so you don't make a mistake. And the entire thing is the answer, not just this part here. Because I also have to do 3 times the inverse Laplace transform of that thing. Okay? The first one I did use this property too. So last slide for lecture B, here's the graph of the solution. If we graph the solution, we see something strange happens at t equals 2 when the light switch goes on. Graph the slope field and the solution. Slope field in red, solution blue here. Y of 0 is 3. Yeah, something weird's going on there at t equals 2. Wait a minute. The solution is not even differentiable at t equals 2. How can it be a solution of a differential equation if it's not differentiable at a point? Is that okay? Is that legal? You know what I'm going to say next. Like Darcidius, we say, we will make it legal. Okay, yeah, there's a discontinuity in the derivative of the solution at t equals 2. There's actually also a discontinuity in the vector field at t equals 2 along this vertical line there. Just don't worry about it. Get a solution when t is less than 2, get a solution when t is bigger than 2. Hey, these solutions do have the same limiting value as t approaches 2 from the left or from the right. The limiting value is the same. So we may as well fill in the discontinuity if there was one. Get a continuous function. Yes, it doesn't technically satisfy the differential equation when t equals 2. But this would be the best thing to think about as a solution overall. Okay? Pretty cool. I hope you liked it. See you later. Or thanks for watching.